Okay, picking up, let's see what we have next. 20 meters to feet. Oh, that should be pretty easy. Number 9, 20 meters to feet. I'm willing to bet that there's there's a conversion factor between meters and feet, and there we go. 1 meter is equal to 3.281 feet. Okay, this is linear units. I'm going to put a dot there just to make sure that we get to use at least 2 significant figures. And so let's see, 20 meters with a decimal point. That's equivalent to being over 1. And we have our conversion factor, and we want the unit in feet. That means that the 3.281 feet needs to go on top, and the 1 meter in the conversion factor needs to go on the bottom, so that meters will cancel with meters, and we get feet. Now, 20 times 3.281 would be 65.62. 3.281 feet is per meter, is a conversion factor between English and metric units. So that is not exact. It is for significant figures. The 20, because I put a decimal point after it, as it does have in the original sheet, that is 2 significant figures. Sorry, so our answer has to be 2 significant figures. The 6 and the 5 can stay, but the 6 and the 2 have to go. The first number you're dropping is the 6. That's 5 or greater. So the number before it has to go up by 1. So 66 feet would be the proper answer to the proper number of significant figures. Oh, sorry. Okay, and finally, number 10. Find the area of a room that is 10 feet by 12 feet, but find the area in meters. Square meters, that is. Oh, okay. Well, let's see. There are a couple different ways you can do it. One way would be to find the area in square feet first and then convert to square meters. Okay, that's better, sorry. The other way would be to do it the other way around. Convert 10 feet and 12 feet into meters and then just multiply them together. So let's try it the first way first. Find the area first in square feet and then convert to square meters. So the area is length times width, which in this case would be 10 feet by 12 feet. And 10 times 12 is 120 square feet. Let's see. This is a preliminary answer, so you don't have to change it for significant figures. So you can leave it as 120. In fact, 120 without a decimal point, that is 2 significant figures anyway. Sorry, just a sec. Okay, so that is 2 significant figures anyway. So that would be no problem with the significant figures anyway. Now that we have square feet, we need to convert square feet to square meters. Looking at the conversion chart that we have, there are no conversions in here for area. So actually what you have to do for area is you have to do it the basic way, use linear conversion factors and square them. So in this case, we would be looking for a conversion factor between, let's see, feet and meters. And then we just square it. So let's see, feet and meters, there we go. About halfway down under length, 1 meter is equal to 3.281 feet. Okay, feet would have to be on the bottom, so it's 3.281 feet for 1 meter. And then you square it. Okay, just to be sure we don't forget, I'm going to circle that too. And we've only, I mean, it's not that far in the future we're going to be doing this, but square feet cancel with square feet. Square meters will be the unit. And remember that this too applies to the number also. So you're dividing by 3.281 to the second power. And you can do that like this. Okay, 120 divided by, I'd use parentheses just to be sure, 3.281 to the second, did I say third power? Second power. And close parentheses and then hit equals. And you should get 11.1472768. Okay, obviously that's way overboard on the significant figures. Look back at the numbers that you put into this calculation from the very beginning. 10 with a decimal point is 2 significant figures. 12 is also 2 significant figures. That's the answer from the first part. 3.281 is 4 significant figures, so 2 it is. That means it's 11, and the first number that has to go is a 1, and that is less than 5, so you can leave the numbers that we're keeping alone. So 11 square meters it is. Okay, that's one way to do it. The second thing would be just to convert the length and the width to meters and then just multiply them together. So 10 feet times the conversion factor between feet and meters. There's 1 meter for every 3.281 feet. Again, feet go on the bottom, so they'll cancel with what we had to begin with. And we get meters as the answer. So 10, I shouldn't need to do this with a calculator, 32.81, sorry, 10 divided by, okay, not multiplying, dividing. 10 divided by 3.281. There we go. 3.04785 meters. This obviously is way beyond the number of significant figures we're going to be able to use because 10 with a decimal point only has 2. But like I said, it's actually better to use more significant figures than you're going to be allowed in the intermediate steps and then round off at the very end. Otherwise, you may end up rounding off too much if you round off at every step. And the same for 12 feet. Feet cancel. 12 divided by 3.281 is 3.6574 meters. So essentially, you see what we've done is we've divided by, or we've multiplied by 1 over 3.281 twice. Well, that's actually what we did up here, because that's what squaring it means. We multiplied by it twice. So we're doing the same thing, we're just doing it in a different order. So the area is going to be 3.04785 meters times 3.6574 meters. And we'll see what that is. 3.04785 times 3.6574 equals 11.1472 blah, blah, blah. And because we're only allowed 2 significant figures, that means this rounds off to 11. Just like it did before. So we end up with a number that's to the number of significant figures we're allowed to use here, it's exactly the same. And you notice that the numbers didn't start diverging until well after the numbers of significant figures were allowed to use. You can get like 3 or 4 numbers beyond the first 2 before you start seeing a difference in these 2 numbers. And at that point, though, the numbers are not real. We don't really know these numbers way out here at the end. That's what significant figures are all about, making sure that you only report the numbers that you do know for sure. Okay, so that's that for that page. The next thing that you have in the math packet is, I believe, a page that's titled 5 Famous Physics Formulas. And that is about 3 variable equations. And so we'll do a little introduction on that before going over the next sheet in the packet. So for 3 variable equations, first of all, what is a variable? Variable it's a letter or a symbol that represents a physical quantity in an equation. Okay. Basically, once the equation is solved, when the equation is solved, the variable is usually replaced with a number. Like x equals. X would be the variable, and you're hoping, in most cases, to put a number on it. There are a couple standard ways of writing 3 variable equations. And one of them would be in the form of something like A equals B times C. And another way would be in the form of something like D equals E over F. And of any proportion like that, something over something else can be thought of as a ratio. And in fact, for any given 3 variable equation, you can go from one way of writing it to another, depending on what you're trying to do with it. You might have an equation that's normally conveyed in this form, but you might have to rearrange it into a form that looks more like this in order to solve for the variable you want. I mean, obviously for this one, if you want to solve for A, then you use the equation in this form. But if you want to solve for B or C, then you're going to end up with something that looks more like this. And we'll see how to rearrange those equations in a moment. In case you don't remember, you've probably got some experience doing that, but might need a refresher. Okay. Let's see. And physical quantities in general have both a variable and a unit. And the variable, of course, as I mentioned, represents a number. So at some point, the the variable will be replaced by a number. So an example of that might be area equals 4.5 square meters, with A being the variable standing for area in this case, and the number, and the unit. Okay, and of course, if the unit is a metric unit, then you might find metric prefixes being used with the unit. So this could be, say, square millimeters instead, something like that. Just to make it official, we'll mention what an equation is too. And an equation is just a mathematical relationship between two or more physical quantities. Okay, so an equation is one of the ways that you can represent scientific laws. In most cases, there's an equation that goes with the law. And you're basically saying that one thing is equivalent in magnitude to something else. Or maybe one thing is equivalent in magnitude to a combination of other things. Okay, equations are sometimes referred to as formulas, so you could do that too. And for more on three variable equations, you can use the triangle method to basically set them up and rearrange them. The triangle method actually makes it really easy to rearrange three variable equations. The catch is that you have to remember how to set it up in the first place. A lot of people tend to set them up incorrectly, and if you set them up incorrectly in the first place, then it basically screws up everything from that point on with that particular equation. Okay, so let's see. The triangle is normally set up like this with three compartments. And let's see, if two things are next to each other, then you see that as multiplying. And if one thing is over another, then you tend to see that as dividing. And I just put a little slash there like you'd use if you're representing something being divided by something else. So for example, if the original equation is A equals B over C, then you would note, especially the B over C, that means B goes on top and C goes on the bottom, and A goes in the other space. So we can see A equals B over C, but we can also rearrange it for, say, B. B is equal to A times C. C is equal to B over A. And this makes it really easy, and you don't have to spend a lot of time. Well, actually, once you're dealing with real equations, with real quantities and real units, you can actually rearrange the equation fairly easily, not quite as easily as this, but fairly easily just by looking at how you can combine the units that go with the various variables so that you get the units that you want for the answer. And if you do that, then it usually works out pretty well too. Okay, so to solve for A, you can just think of covering A, and you're going to see basically what A is equal to. So one quantity in the equation would be what's under your finger, and the other quantity would be what's equal to it in terms of the other two terms. So if you want to solve for A, it's B over C. If you want to solve for B, it's A times C. If you want to solve for C, it's B over A. So pretty simple, actually. If you have another equation like D is equal to E times F, then you can set it up like this. E times F means they have to be next to each other on the bottom, and D would be on top. Okay, so very often you look at the right-hand side of the equation, the things that are actually multiplied or divided together, you decide where they go, and then the other thing goes in the empty space. So we now know that D is equal to E times F. E is equal to D over F, and F would be equal to D over E. So now you've got all three equations for every possible relationship among those three quantities, and it's really easy. So for an actual example, say the area is equal to, the area of some surface is equal to 12 square centimeters. The length is equal to 4 centimeters. And what's the width? Well, hopefully it's not too hard to see that the width must be 3 centimeters because 4 times 3 is 12. But we can also look at one of these triangles. We know that the equation is area equals length times width. Length times width means that those two terms have to be next to each other, which means they have to be on the bottom, and then area would be on top. So area equals length times width. So if you want area, it's length times width. If you want length, you cover that up and it's area divided by width. If you want width, you cover that up and it's area over length. What we wanted was width, so that's area over length. Which would give you 3 centimeters. 12 divided by 4 is 3. Square centimeters divided by centimeters would be centimeters to the first power, because when you divide things raised to a power by the same unit to a different power, the power of the answer is just going to be the top power minus the bottom one. So if you take centimeters to the second power divided by centimeters to the first, your answer is going to be centimeters to the 2 minus 1 power, or in other words, centimeters to the first, which is exactly what we got. Another example could be the speed of a moving object is 20 meters per second. How much distance can one object cover in 14 seconds? All right, so we can look into that. We have speed is equal to distance divided by time. Normally this equation would be given to you, but in some, in some cases you really don't even need to be given the equation. You could just see from the units of speed, meters per second, that's units of distance divided by units of time. So, speed you would expect to be distance divided by time. And that's exactly what it is. Okay, so we can set up a triangle. And we have S equals D over T. Again, look at the side with two terms on it. D over T means D goes on top and T goes on the bottom. And S goes in the empty space, which is on the bottom. So we have this speed is equal to distance over time. Also, if you want if you want distance, that's speed times time. Or if you want time, that's distance over speed. And what we're being asked for is distance. Distance covered in 14 seconds. So we know that distance is going to be speed times time. Speed is 20 meters per second, and the time is 14 seconds. You can also watch the units to make sure that they're coming out right, and that's what I meant about once we see actual problems with actual units, you can just arrange things so that the units come out right. If you take something in meters per second and multiply by seconds, the seconds will cancel and you'll end up with meters. That's a distance. And that would be 280 meters for the distance that's covered. And significant figures here would be 2, because 20 with a decimal point is 2 significant figures, and 14 is also 2. And 280 without a decimal point is also 2. So there you go. Units work out, the triangle works out, everything's good. Okay, I'm going to cut off the second segment here, and we'll get to the 5 famous physics formulas in the next segment. See you in a minute.